Welcome to Cranfield University and the Institute of Mechanical Engineers to this live session, slightly later than we thought, so bear with us. Thank you very much for sticking around. In the next 30 to 45 minutes, we're joined by Rosa Wilkinson. I'll come back to Rosa very shortly. As I say, my name is Toby Thompson. I work at Cranfield University. We're also joined in this next period by some people in a laboratory here at Cranfield University, and it's a welding laboratory. So I'd like, if you could, Philo, to wave at camera. We're joined by Filomeno Martina. There he is. Give us one more wave, if you could. So your chance is to be able to ask Philo some questions, live questions on this session. And the last person we're joined with here today is Richard Tiplady, Chairman of the IMechE Oil, Gas and Chemical Committee. And Richard's going to give us some information about traditional manufacturing methods, and we're going to compare those with what Philo has there too. So let me go back to Rosa first of all. Rosa, you're, let me get this right, from the High Value Manufacturing Catapult.
That's right.
What on earth is that?
Well, do you know, it's an organisation that I wish an awful lot more people knew about.
I don't.
Well, let me tell you.
Thank you.
Very simply, what we do is we work with businesses of all shapes and sizes, businesses that make stuff, and we help them harness the new knowledge, the new technologies that are coming out of our amazing universities and research base here in the UK. And we do that because we believe that where they can capture the value of those new technologies, they can catapult their performance into a completely different league. They can make themselves more competitive, more productive. They can tackle issues like their environmental impact. They can make products that have an advantage over those that the guy down the road is making, or more, the guy in another country. They can really improve the way they do things.
You said businesses. Are you looking at manufacturing businesses? Who are you talking to?
Well, manufacturing businesses, but manufacturing's a pretty broad church, you know. Let me ask you a quick question.
Uh-oh, go on.
Okay, who do you think are the biggest manufacturers here in the UK? What's the biggest bit of the manufacturing
I'm thinking,
sector?
and help me out here, and please, we want your questions on the text chat on YouTube. I'm thinking motor manufacturing. I'm thinking metal bashing. You're going to say no now.
Well, you know, they are incredibly important industries. They attract huge investment to the UK, great employers, but they're not the biggest. Food and drink industry. You know, think about all of the things that you consume, all of those products in your kitchen. Think about their packaging, think about their formulation.
You don't think of them as manufacturing?
They are manufacturing, absolutely manufacturing, and we work with an awful lot of them. Indeed, our Manufacturing Technology Centre over in Coventry, we have 7 centres around the UK so that everybody can get to us, are working with the Food and Drink Federation to make sure that we are helping them to be the best they possibly can be in this very competitive world.
So what do they come to you with? With a problem? With an idea?
Do you know, it could be 101 different things. Sometimes a business will come to us because they've heard that Joe Bloggs down the road or in another country is doing something that makes their product more attractive, cheaper, more efficient to produce, lower waste, all of these things. And they'll say, I want some of that, can you help me? Sometimes they'll come to us with a specific idea and say, I want to do this with my product, can you help me?
So they have a clear idea as to what they want to do?
Absolutely.
Right.
And sometimes they'll come to us because they know that they need to improve their production process, particularly at the moment in digitalising manufacturing. They recognise that if they can apply some of the digital technologies to what they do, they can connect better with their customers, they can spot problems on their production lines before they happen, they can monitor their stock usage, they can make sure that they've got supplies coming in at the right time. Real opportunities for firms doing that sort of thing.
They sound like challenges that the businesses are facing. What are the other challenges that you come across in your work in the Catapult?
Do you know, one of the things that I see day in, day out, and it's certainly something that I've experienced even before I joined the Catapult, is that actually the process of innovation is scary.
Scary?
It's scary.
Because?
Because it involves potentially lots of money. There are very few guarantees of success. If you're doing something new, how will you know that it will work? If you do something new and you convince yourself that it will work, how do you convince the people that you're selling to that it's good for them too? Really big issues if the people that you are selling to are, for example, making aeroplanes.
Presumably, how do you also convince investors to invest in your product if you don't do your products up to scratch?
Absolutely. An investor will want to be confident that they can get a return on their investment. if they can see that a new process or a new product has been tested, has been shown to work, has been proved out at a factory floor scale test, then they'll be more confident that their investment will actually produce a dividend for them. That matters. We do give people confidence. Take away the risk, build in a few guarantees.
You heard it here first. We want, please, your questions, your comments, your observations. Please type them in to the relevant box. Rose, we're going to come back to you. Hopefully you've got some more questions, I think, for Philo. We're going to hand over now to Richard Tiplady, who, just a reminder, is the chairman of the IMechE, the Institute of Mechanical Engineers, Oil, Gas and Chemical Committee. So Richard, those challenges that Rosa was talking about, do they sound familiar to you?
Yeah, quite definitely. We, as an industry, we are unbelievably conservative. We don't like change. We need assurance. We need to know it's safe. We need to know it's tested. But our industry is full of metal items. Process plants are full of metal items. And what I'm going to do over these next few minutes is just run through some of those types of items. So on the next slide, I'm going to show you some traditional commodities, bulk manufactured items like valves. Are invariably cast bodies or forged bodies, machined when we need to have hard-faced wearing to cope with erosion and wear and tear. They have a weld overlay as per that ball you can see there in the picture. And the valve seats are manufactured out of a harder material and inserted into the casting. So generally, an easy manufacture, many years of experience to making these things, and not ridiculously costly. But now we move on to the next slide. This is the other end of the scale. This is the bespoke items, the one-offs. This 1.2 metre diameter valve, butterfly valve you can see here, is manufactured, it's fabricated out of plate, rolled up, welded together, machined. And the areas requiring wear protection, you can see on the disc on the top right, which is once again manufactured by welding and fabrication, is a weld overlay. Long, laborious, time consuming and very, very slow lead time. There's an example at the bottom where the hard facing in this case is done with refractory material. So just to show the complexity of our bespoke items. Now obviously there's a massive difference in value between those items and the first items I showed you on the first slide. Now moving on to the next slide, what we have here is something used more in the chemical side of the process. We have mixers, injectors. The piece of corrugated iron to sort of on the bottom left hand side is a mixer, static mixer in flow. So as flow goes through the pipe, those baffles are just churning things up and mixing them. Very, very simple and crude, but serves a purpose. The mixer on the right at the bottom is a screw mixer. By the screw, the counter-rotating screw, that pushes material through and mixes it together by shear loads. Now that screw there is a forging that has been machined, ground. You can imagine the profile of that grinding is actually quite critical to how the screw works because the clearance is what makes the shear action. Once again, a ridiculously long lead time for these components, but there aren't many of them. There aren't many identical items. We're talking numbers of production runs of 5 or 6.
So Richard, can I ask you a question? That screw that you have there in the bottom right of your image, that would have taken how long to plan to make and how long to make?
If it's for one-off bespoke design and then single use, I would say these you're talking into 24-month lead time from design through to delivery. Ridiculous amount of time to deliver a component, but the component is very detailed engineering. The time to get the forging made is long. Waiting for forgings is a long process. And it's got to be right because with such a long lead time, any faults, you step back right to the beginning and start again. So it is a long lead time. Right, moving on to the next slide, this is our most expensive piece of equipment invariably on a process plant, the rotating equipment. These are a mixture of all sorts of manufacturing. They're forgings, they're machined, they're castings that are machined. On the rotor, the impellers are shrunk on because the metallurgy of the rotor is completely different to the metallurgy of the shaft. The bearings and the seals are different metallurgy. There's so many different metals and metallurgies in this component. A lead time of a bespoke piece of rotating equipment like this can be 2 years for something as small as that. Obtaining spare parts, long lead time. Invariably, most operators have to maintain a spares holding for these because of the lead time on the spare parts. Once again, a lot of different metallurgy in there and a very labour-intensive construction, a very time-consuming construction method. But as I say, we're a very conservative industry. We don't like change. Those compressors like that have been in the industry for many years. Small changes are made in a controlled manner, but there's years of experience, years of knowledge. So we're now at a point where if new manufacturing techniques are coming along, we need to give confidence. So on a final slide here, we've got, I don't think some of the new manufacturing technologies are going to give us a big return on our bulk commodities. There's been many, many years of manufacturing experience. It's a competitive market. You can buy valves from numerous suppliers worldwide. Very competitive, so they have driven the prices down, they've driven the manufacturing methods the best they can. Where the benefits for my industry are, which is, as I say, very conservative, is in the bespoke items. Items that go offshore on offshore oil platforms have to be very much weight controlled. So we don't want to be sending excess metal offshore. We want to manufacture things to exactly the right thickness, the correct thickness. We have to optimize the metallurgy. If you imagine any piece of process equipment, you need the strength and ductility of the body to hold the pressure in, to hold the temperature in, but we also need the wear resistance, we need the corrosion resistance, we need erosion resistance on the internal wetted surfaces. The metallurgy can be quite different. So we can have a chrome moly steel as the pressure body, and we can have a stainless steel cladding on the inside for erosion resistance. So those differing metallurgies are a great challenge to us.
So is it fair to say, Richard, that the picture you paint isn't actually overly positive in terms of flexibility, in terms of return, in terms of quickly designing and producing something? You're not painting a very rosy picture there.
Oh, there is nothing quick about bespoke equipment in our industry. Many projects, the very first thing you have to do is design the piece of major equipment, get the procurement going, and then move on to the rest of the project. It becomes the very first thing you have to do is to design and specify that first piece of equipment because of the lead times, because of the time it takes to get the forging booked into the forge masters. It isn't rosy, and it's not very good at responsive fast track. It's not very good at letting us chase market opportunities, and it's not very good to make us competitive.
Sorry to interrupt you there. Your background is oil and gas,
Yeah.
but I presume you're saying this applies across beyond the oil and gas industry.
I'm personally oil and gas, but when I work in the IMechE, we work on the Process Industries Board, where we have food manufacturing, as Rose has mentioned already, major industry. We have bulk handling. We have pharmaceuticals, very high value industry. The British economy has a lot of influence from the pharmaceutical industry. We have offshore oil and gas. We have onshore chemicals. We have gas production. Full range of process industries, and these all apply to those process industries the same. One final thing we can do with modern technology is we can make the designer's requirements reflect in the product. If you refer back and recall the shape of that baffle, there's a process engineer has developed the process flow. Process flows over baffles it generates a lot of fatigue, a lot of vibration. Welding together pieces of flat steel to make the baffles is not optimum. It's not the optimum profile. If the design engineer's computerized fluid model ideally would like to have a different shape profile, for ease of manufacturing we use flat bar to make it. If we could make a manufacturing system where we could follow the optimum design, items would end up being smaller, lighter, more effective, and quicker lead time. And that's what we need to do. And what we will also deliver is better reliability. Because if we design and manufacture to the correct design, the correct pressures and vibration forces and everything else, then we'll have reliability. So there is opportunity, but as I say, we are a notoriously conservative industry.
Rosie, you've got a question for Richard?
I do. I'm fascinated in that. You started off by saying, Richard, that you were a very conservative industry, and I recognise that you are, but you're conservative for a very good reason. People do not want disasters of the sort that have hit our newspapers in the past. So any change is a risk. How do you make sure that any change isn't going to lead to some of the environmentally catastrophic things that we've seen in the past? It's a really big deal for your industry.
In the industry, it comes under the high hazardous, the COMA regulations, high hazard installations. Everything's brought into service, whether it's new or a minor change. It's fully HAZOPed, it's assessed, risk assessed. Equipment is tested to destruction, it's tested in manufacture, it's tested in service. I don't believe we would straight away throw a new component manufactured completely differently into service. It will be put through a pilot testing and strength testing, and each change is assessed and documented, and that's how we control risk. We control risk all the time in the high hazard industries, and we need to, when we make changes to manufacturing, that's the same as changing the process. We assess that risk.
And there are certainly some that would say not making the change is actually leaving existing risks more open than they should be.
Yes, because we also will be able to address poor reliability issues and fatigue and fracture issues as well.
Richard, can I ask one last question before we pass over to Philomena and the laboratory and some fantastic looking stuff in there? There's a question, what are the main challenges, researches in the UK and which industries? And that applies to you. Another question is, what are the latest achievements and innovations in wire and arc manufacturing?
Well, the latest one, let's see what Philomena demonstrates to us before we discuss that second question. We do have a difficulty in the industry, in the process industries, bringing research to the industry. As the industry, the operators are the end users. There are engineering specifiers and there are engineering contractors and designers. We need to bring the research in the front end, and I think this is where Rosa's organisation can really help our industry. Get that knowledge and pass through, and the knowledge and the benefit brought all the way through the supply chain. We don't necessarily just go and buy a component. We're not walking down the road to a car shop and buying a car. We engineer it, we specify it, somebody fabricates it, somebody installs it, somebody else tests it. And we need to join this together, and I think this is where Rosa can really help.
Do you know, one of the things that I know from my time working in inward investment is that the UK is highly regarded around the world for the quality of the knowledge that is being produced by our absolutely unequalled research base, our universities and others. Now, one of the things that we've not been very good at in the past is harnessing some of that knowledge and translating it into something that works and pays the bills here in the UK. And I think what we do in the high value manufacturing catapult is just what you've described. It's about holding people's hands as they apply that knowledge in their own environment so that their bottom line, their performance is very, very significantly enhanced.
Yeah. Wow. Yeah, hold that thought. Hold that thought. Sorry, Richard. I want to go to Philomena now. For those of you just joined the session and you're wondering quite what you've stumbled across, you're getting a live feed from Cranfield University in association with the Institute of Mechanical Engineers. So Philo, hopefully you're still there in the laboratory. We want a bit of a tour. We want to see a little bit about where you're at. But if you could first start off by saying who you are, how you got into what you're doing, and then explain quite where you are. There you are. We can see you now.
Thank you, Toby. Welcome to Building 46. That is the home of the Welding Engineering and Laser Processing Center. I work here as a senior lecturer in additive manufacturing here. I've been in Cranfield for about 10 years. I came as a master's student, actually, a double degree student. I started doing my MSc thesis on this topic of wire and arc additive manufacturing, which is what I'm going to talk about today. And then I decided to make it my career, which is why I'm still here today. I mentioned additive. Thank you. I mentioned additive manufacturing. What is AM, or as you might know it already, 3D printing? As the name suggests, is a process which is based on building objects in a layer-by-layer manner. And it's actually counterposed to other manufacturing technologies, like, for example, subtractive manufacturing. In order to have an AM or a 3D printing process, we need three main ingredients: a heat source, a motion system, and some sort of feedstock. And if we combine these three in a number of ways, we give origin to a wide range of processes. For example, we can look at processes based on a bed of pre-placed powder, which by using a laser heat source can generate highly complicated, optimized structures which are net shape. So in theory, the geometry is exactly the one you want it to be as soon as the manufacturing process is finished. However, these processes are extremely constrained in terms of cost. Machinery is expensive, raw materials are expensive, and also speed and size, which are both very, very small. If we look at the slide that Chris can put up right now, there is quite a convenient way of comparing a variety of different AM processes. And if we go back to what Richard was saying, in terms of attracting the business opportunities for parts which are large, big engineering structures where cost savings are important and excellent mechanical properties in the as-built condition is key, as well as part scalability, we are left pretty much with the choice of wire and arc AM, or WAM, as a process of choice. And that's what we have been doing here at Cranfield since 2006. Thank you, Chris. So as the name suggests, WAM is based on wire instead of powder as feedstock, and this enables substantial scalability of the part that we can make. We can make them much faster. Instead of building at 100 grams per hour, we can, for example, build up to 15 kilograms per hour. We can make these parts as big as you want, as I will show you later, and of course for a much cheaper way. Here we've got only a few of the many demonstrator parts that we've made throughout the years for our research partners. For example, this outboard landing gear rib that we made more or less 8 years ago for Bombardier. Traditionally, this part would be machined out of solid or of a very rough forgings. You would start from a billet of over 250 kilograms in mass. You would spend quite a lot of time machining it away, removing this fantastic titanium in the form of swarf until you are left with the final geometry. And of course, that swarf can be recycled, but just to give you an idea, we might buy billets for 60 pounds per kilogram, and we sell that scrap for 60 pence per kilogram. So there is quite a lot of waste in money associated with that. By doing it in additive, first of all, we can compress the lead time associated with forging. Typically, you would have to wait 12, 14, 16 months for the forging to be delivered, plus the machining. While in additive, which is a process that's digital in nature, all we need in theory is a starting substrate and some wire as a feedstock, and we can build any shape that we want, provided we've got the initial CAD file. And so we can build this object in less than 30 hours plus machining. The reason why I keep mentioning machining is that our processes are so-called near net shape, meaning that the geometry out of the printing process is not quite the final one. A finished machining operation is required, but even so, we save quite a lot of time and a lot of money.
Philo, can I ask you a question? There's a question just come up.
Certainly.
It says, sounds like the resistance and adoption of WAM comes from uncertainty in industry. Do you think that once several industries adopt WAM in the mainstream, the manufacturing technique will boom?
Yes, at the moment, the reason why WAM is not becoming mainstream just yet is that we've been very ambitious in targeting highly critical components. So we're not building small brackets for your television in the business class of an aircraft. We are building landing gear ribs or wing spars or highly important and structural elements. And therefore, before we can see this process rolled out in industry, we need to build that confidence in the structural integrity. Having said that, there has been quite the upkeep of WAM in industrial design and civil engineering, and I think early next year, a bridge which has been 3D printed will be installed in the red light district in Amsterdam, actually.
Wow.
So WAM is getting out there. And at this point in time, we are working very closely with the OEMs, for example, in this case, aircraft manufacturers. We are about to start making a 200 kilograms landing gear rib in one of the cells here on campus in this building. And before we started with the proper manufacturing of this landing gear rib, we've done a couple of test pieces to make sure that certain features could be produced with the required integrity. And that's the typical journey that we put in practice.
I think Rosa has a question for you, Philo, if you can tolerate another question.
Yes, please.
Indeed, it was picking up some of the points that you were making earlier, Philo. You were saying that actually this process cuts out some of the waste, which we know is huge in some of the processes that you've been describing. It also makes things an awful lot faster. So already we can see that there's a competitive advantage for those manufacturers who apply it. But I would say that there is also an environmental impact that we need to think about. Certainly, it sounds to me as though you will be helping their environmental footprint, their impact on this earth that we all share, which sounds like a good thing. But one quick question. How do you recycle the products at the end of their use?
Good question.
It depends very much on the alloy that we are talking about. Actually, one of the reasons why titanium 64, which is the alloy that we've used for this material, is indeed the workhorse of the aerospace industry, is that once you have machined it away in the form of swarf, it can actually be recycled in a straightforward way. It is still quite energy intensive as a process, but it can be recycled. The same applies to most of the steel alloys and to some of the aluminum alloys. The challenges are for some special aluminum alloys which have been alloyed with some rare earths, or, as I will show you later, when we build structures made of several materials into one. And this is very much subject of painstaking research in other departments here on the university.
Great, thank you.
Super, thank you.
As you were touching upon the topic of emissions, let me give you some number. If we could switch from design for manufacturing to design for function, for example, by optimizing the shape of an object and reducing its weight, let's say by 1 kilogram, and this part was supposed to fly on an aircraft, just with that 1 kilogram we could save over 100 liters of fuel per year, which is more than 400 kilograms of CO2.
That's
so
what
we are working really closely with the industries in order to maximize these benefits in terms of flying object, but also in terms of objects which are here on the ground. I'm going to give you an example of this pressure tank. Actually, this is for space applications, but we have made several more for other sorts of applications. In this case, we can enable a number of advantages from a business point of view. First of all, if made traditionally, this tank would be made out of 3 different components. You've got the main ring, which is machined out of a forged ring. Then you've got the bottom dome, which is machined from a separate billet. And then here you would have a conduit, which is where the fluid is drawn out from. Instead, again, by maximizing the manufacturing capability of additive, we've decided to start from a commercially available rod, really easy to get hold of. That's our substrate. We then printed on it the dome, and then we continue with the deposition of the actual main body of the cylinder. So instead of having 3 separated components and the associated supply chain, now we can do everything in one go. Then we go from the preform made by WAM to the finished machine component, and by doing so we can reduce the amount of titanium which is wasted by over 200 kilograms for every tank that we made. The tank also happens to be 60% cheaper to make, and it could be made really in a number of hours as opposed to several months. And just for your information, that's how the tank will look like after it's been finished machined. In particular, this actually is a fuel tank for a satellite. Another attractive point for this component was that because you are no longer constrained by the set of forging tooling that you need to have if you go down the traditional route, now you can change the shape and the size of your tank to match the requirements of the mission. So again, you can minimize the amount of fuel that you take to space. And again, each kilogram that flies to space is about 10,000 pounds. So if you can reduce some weight, you're also reducing your expenditure.
Can I ask you one more question, Philo? Some other questions
Certainly.
just come in. Do you have experience in duplex stainless steels? What are the challenges for this material?
We have deposited some of it. It's not quite as mature as other alloys like titanium 64. The challenge is in that particular class of steel is to achieve the right ratio of the various microstructure which you would have at room temperature once you're done with the 3D printing processes. And in particular, the corrosion properties depend on this ratio. And that's quite hard for us to achieve because our first preoccupation is to achieve the right geometry and to do so without producing defects. But we've got quite a lot of interest from our industry partners in the oil and gas and processing industry. So it's something that we're very actively working on, also by tuning the heat input that we provide using multiple energy sources, as well as developing new materials for this process. Because so far we've been using traditionally and commercially available welding wires, and this is no longer welding. The kit might look the same, but actually is a very different way to go about making parts. As we were talking about oil and gas just now, that's one of the most challenging parts we have made. It's an elbow for a flow loop. Typically, this part would be made as a pipe, and then it would be bent once it's been taken to high temperature, and then you have to apply a protective layer to mitigate the risk of corrosion. We've done this shape in one go by additive. The idea is that if the designer gave us the final shape, the final optimized design of the entire flow loop, this component would be no longer made out of several 90-degree bends, which are then joined together to straight bit to take the fluid from A to B, but we could have a nice elongated component which minimizes the pressure losses in the duct itself. And then crucially, because our process is open in nature, we can feed more than one feedstock at the same point of deposition. And in a related project, we have proven that we could build some of these shapes already with the protective layer for corrosion resistance inside, so that you have one step for both materials that give you the right geometry and the right properties.
We have another question about machining, if you can take that one. As the WAM
Yes.
process evolves in capability, what do you think would be the major hurdles in integrating it with conventional processes like machining?
From the practical experiments that we have done so far, as we move more and more towards real case study, you have to keep in mind that we try to minimize the amount of material that we deposit. This means that we've got our initial CAD file, and we normally apply an envelope of 1 to 2 millimeters around it to enable the finished machining of the waviness. And therefore, it is quite critical that when you are taking the part out of the WAM system into your normal machining center, be it a lathe or a milling machine, you position it in the right position, otherwise you would not be cleaning up the material where you want it to clean. But of course, in our case, digital technologies, for example, laser scanning and other metrology methods help us, because we can deposit the material, take a nice scan of it in a quick and inexpensive way, and then we know exactly how to set up that part on the machining center. And of course, between one and the other, typically we would have to recur to a stress relieving heat treatment to reduce the residual stress and the internal tension, but these are established processes that have been around for decades. As I was mentioning multi-materials, I'm just going to give you a quick example of a specimen made in a graded way from steel to a copper-based alloy. Provided that the two materials are metallurgically compatible and they expand and contract in a comparable way, actually it's quite straightforward for us to go from one to the other. We have already achieved it, for example, going from steel to Invar for carbon fiber reinforced polymers tooling. So in this case, not for the production of the actual part, but for indirect application, the tooling. But also for more exotic applications, for example, for the nuclear fusion industry, where we can go from moly to tungsten to tantalum and so on, which is something that you can see here. And then finally, in terms of going forward, looking at how we can expand the geometrical capability of this process, we've been working very recently on dies for automotive application. This in particular is for the press forming of the A, B, and C pillar of your car chassis, as well as using other heat source, like in this case, where we can deposit using a laser instead of an arc, and we can deposit much thinner structures, which crucially do not require any finish machining after they've been deposited. At this point, I think you guys must have had enough of the parts and probably want to see the machines where these parts are
I want to see
made.
what does a typical machine look like. Can you show us one of those?
So, as I said, 3 ingredients, motion system, feedstock, and heat source. Typically, we like to use anthropomorphic robotic arms to provide the system, which is what you can see on both sides of me. These anthropomorphic robotic arms are most likely what have also built and assembled the car that you drive every day to go to work. So they are really established bits of kit, very reliable and easy to source. We can configure them in a number of ways. We have been chasing the possibility of making larger and larger and larger components. So in order to enable that, we said, let's stick them onto tracks so that they can slide as they print. And this process, or this approach, proved to be quite successful. The overall breadth of this cell is around about 10 meters. And I think in 2016, we were able to print a 6 meters long aluminum spar as a feasibility study. And as far as we know, that is still the world's biggest part ever 3D printed in metal in one go.
Wow.
The other attractive point of robots is that they are very flexible in nature, and therefore we can equip them with automatic tool changers. For example, in this case, what you can see on the left-hand side is where the magic really happens. This is our so-called end effector. At the center of it, at the heart of it, if you wish, there is a plasma torch, which is where the heat is generated. And then what you can see around it, it's a box. It's a special box that we called local shielding device. Now, for most reactive materials like titanium, typically you have to print them or weld them under inert atmosphere, and this can be either provided by argon or nitrogen or helium, or even further by pulling a vacuum inside the entire chamber. And of course, that's very much possible, but it presents challenges in terms of scalability. Imagine having a bag or a chamber around the entire kit that I'm working in at the moment. That would be very impractical. So we developed this box, which thanks to a clever design of plenum chambers and laminar flow tubes, produces that inert atmosphere only where the material is hot enough to need it, therefore at the bottom of its surface. And once the shielding device has moved away, we know that the material is cold enough not to get oxidated, therefore pick up oxygen anymore. And in this way, we've been able to print structures for fast jets, for example, Typhoon, that were over 2 meters in width and 1.5 meters in length, which is again a world first. Once we've got this mechanical housing.
Cut in there.
Certainly.
You say a world first. It's really great for any business to be able to say that. But as I look at the kit that's surrounding you there, Philo, I see KUKA robots. We're all, I think, pretty familiar with them on every advanced manufacturing factory floor these days. But then you talk about this is the box where the magic happens. Now, if I am a manufacturer, and I've certainly heard what you said about how this technology can really improve my performance, where am I actually going to get my hands on that wonderful box of tricks that you've just been talking about? And who am I going to be able to find who can keep it working for me? How am I going to be able to fit it within my business so that my staff can use it? You know, there's lots and lots of questions around that little box of magic that you've shown us.
It's a very good question, and that's exactly the journey we've been through and the questions that we have been asked by our industry partners. We've been working on this technology, as I said, since 2006. And in order to prove that it was viable, we had to develop all of these aspects in this center. And after so long, we finally have got enough confidence that we can bring them to the market, which is why in June last year, we have incorporated a spin-off company called WAM 3D Limited, whose mission is indeed to enable a smooth implementation of the WAM process. And to do so, we want to provide an integrated ecosystem to our potential customer, which hopefully will have all the answers to the questions you have just asked. So first of all, we are already sourcing the manufacture of the end effector, which has the shielding device, some adjustment of the wire positioning, as well as some sensors to monitor the geometry that are not yet available commercially. And in fact, in this particular case, we can call this a nice story of interdepartmental collaboration because these sensors were developed by our colleagues in the photonics group. We have designed the entire software which does the toolpath planning, the calculation of the process parameters, and ultimately runs the machine. And also we're providing training and business case developments to our end users. So that is exactly what we want to do, because if you're providing only the machine or only the software or only part building services, you are helping your customer only in a fraction of the real way.
So Philo, I've got a question there, or rather for those of you who just joined the session and wondering quite what it is that you're joined into. You're at Cranfield University, live. You're also with the Institute of Mechanical Engineers, the IMechE, who you may know it. I want to find out what that blue thing is and what it's hiding behind you there. Maybe Chris can give us a pan. But before you tell me that, Philo, there's another question just come on live onto the session. Without standardization, the industry will not accept the AM products easily. What are the latest activities regarding standardization of AM products? If that question
there is
makes
quite
sense.
a number of initiatives around the UK, the EU, and also the US. In the UK, the British Standard Institute has been quite active. I've been involved personally in 3 committees, one on the inspection, one on the raw materials, and one on the design of the machines. I've also contributed to writing some design guidelines for DED, so Directed Energy Deposition AM, which is the category WAM belongs to, so that the designer of the future know how to design their parts best for this process. And then also a number of colleagues are involved in some committees of ISO or ISTM, in particular the F42, where standardization is really making good progress. That's a very valid point. We're doing our best by proving that technology is good in terms of integrity and properties, and then the standard hopefully will keep the community happy from a legal point of view and will make everything a little bit more normalized, which is what we would very much welcome.
Wonderful, Philo, thank you very much. We don't have a great deal more time, but tell us what's behind you under that blue tarpaulin, if we can have a little look at that area. Chris?
So actually, Toby, if I was able to tell you what's under here, then this part would not be covered in this blue cover. We work really hard in order to produce state-of-the-art component and to establish ourselves as a World League Institute. And so sometimes we need to take protective measure, because certain things that we've developed in terms of how to mitigate distortion and manage residual stress are quite unique. And
so you're saying that's secret? We can't see, we're not allowed to see that.
I can tell you what we're about to build. It's a cantilever beam. It will be 5 meters long for architectural application. I will be able to show the part once it's done, but at the moment we need to keep it under wrap because we don't want to disclose the way we're getting there.
Well, we haven't got a great deal more time, but any chance you could quickly show us a little bit more about the entire laboratory that you're in there here at Cranfield?
Yes, so this is only one of the 10 facilities that we have in the lab, and I think Chris has got a nice video which can give an overview of some of the other cells. Some of them are based on various other heat sources like arc or lasers, and the lab today is very quiet because we needed to do the filming, but normally there is a lot of activity going on. It's about 35 people of us in the lab doing experiments day in, day out. And sometimes it's stressful, but it's quite rewarding at the same time because every day we find something new and we share it with our industry partners or we publish it. And it's very nice to work in this lab here in Building 46.
Philo, thank you very much. I got one last question that's online here. How do the mechanical properties of WAM components stack up against those traditionally manufactured?
For most alloys, actually, we are just a bit shy of the properties for the equivalent forged material, and that's because we are using feedstocks and materials which were indeed developed and designed for forging. But actually, in additive, you are somehow in between the casting and the forging way of processing metals. So, in an ideal world, we would start from working with materials that have been designed for this process. In the interim, one of the things that we are doing here at Cranfield is to combine the additive processing with a mechanical treatment, in this particular case using a machine hammer pinning process. And what we do with this machine is introducing strain and stored energy in the crystals of the material which has just solidified, just like you would do in a forging operation. And then the subsequent heat provided by the deposition will trigger a change in microstructure. So at the moment we have actually proven that for a wide range of alloys like maraging steel, Inconel 718 or titanium 64, we can produce properties that are comparable, if not better, than the equivalent forged alloy. At the core of this is the baseline excellent structural integrity that we have. As I said, wire is clean and normally yields structures that are 100% dense. So even without the mechanical treatment, we've got a very good starting point to begin with.
Wonderful, thank you. I think, Rosa, you had a very brief question. We're running out of time, but a brief question.
I did. I was fascinated to hear how you're working through your upward supply chain on this, because standards are one thing, but actually making sure that the people who are buying stuff from you are convinced is a very big deal too, not always the same issue.
Good point. Philo, I'm going to just come around, just a parting thought. If you had to leave the audience who had joined us here live at Cranfield University, a parting comment or question even, what would that be from you? So
I think drawing from my personal experience, as I said, I've been here for 10 years and I thought about leaving several times, maybe to go back to somewhere warmer or with better food. And actually, in the last 4 or 5 years especially, I've had the constant feeling that this was finally kicking off, and it's just been getting bigger and bigger and bigger, and we've been getting more and more traction. And what I would like to say is that this way of making things is definitely going to change the way we manufacture metallic objects around the world because of a number of different business reasons, environmental reasons, and so on. So we're all very excited, and I ask you to keep an eye on Cranfield and on 1-3D, because in the next 2 to 5 years, this will really take a massive step in the industry. And hopefully my dream is to print a part here, stick it on an aircraft in an hangar next door, and take off from the airstrip here at Cranfield, and come back in one piece, of course.
Of course, no small ambition there. Philo, thank you very much indeed for your time here. And those of you intrigued as to what Philo was standing in there, please get yourself to Cranfield. Start your journey with us. We have very many courses here at Cranfield. I'm going to talk now just briefly with Richard to find out, Richard, what are your parting comments? What are your reflections on what you've seen that you certainly talked about, and then what you've seen in terms of Philo's additive manufacturing?
Thank you, Toby. What I saw there is a 10 years of research, 10 years of development that's leading through metallurgical investigation. He's addressed NDT, the fact that there's looking into the longevity of these components. As I say, we've got a conservative industry. We need items that are designed for purpose, functional, but also proven to be safe and reliable. And I think the technologies that have been developed here, with the backup and the fact the NDT skills are here, the measuring skills are here, I think it's an excellent starting point. And what we need now is the full supply chain of our industry, which is the specifying engineers, the designers, the fabricators, the bespoke item fabricators, which we have plenty of in this country and plenty of across Europe and right across the whole world, to buy into this technology and start working on it. They will be reaping rewards very soon, and organisations like Rosa's will help that process of bringing everybody on board.
Richard, thank you. And that just leaves me a good segue there to Rosa. Rosa, your parting comments, your parting observations, what do you see?
It's a plea.
A plea?
A plea to manufacturers wherever they are in the UK. Stop and think about how we can make things differently. You know, we don't have to make things in the way that they've always been made. This inspirational technology that we've heard about at Cranfield can save you time, money, allow you to develop products that are better and better for the environment. That will put you ahead of the competition. Please don't have feet of clay. I know it can be scary, but there are organisations out there like Cranfield, and certainly like my own high value manufacturing Catapult, who can help you along the way. The great news is that so much of the knowledge that allows these technologies is developed here within the UK, within our amazing research base. We should all celebrate that.
Wow, excellent plea. You kind of got me excited about that one. There's a few more questions on here, but we don't have time for it today. Please keep those questions coming. If you're watching the recording, and we hope you are, please type those questions into the chat box, and someone at Cranfield will come back to you. Please get yourself to Cranfield if you've not been here before, and or to the Institute of Mechanical Engineers and to the Catapult that Rosa mentioned. So thank you for your time, for paying attention. Sorry for the slight delay in starting. We look forward to welcoming you later on in the year, hopefully. Thank you very much indeed.